Assalamualaikum warahmatullahi taala wabarakatuh. Today we will continue our lecture with soft lithography techniques. In this series, I will introduce you to 4 types of soft lithography technique, which include replica molding, REM, micro contact printing, micro transfer molding, and the last one is micro molding in capillaries. Before I go further to the replica molding or REM, actually this soft lithography is another type of technique where you can transfer your pattern to your substrate instead of using a typical photolithography technique that we have learned before this. Okay, so it is it is more simple and more actually give you another option for you to transfer your pattern. But usually and commonly you will transfer your pattern by using normal photolithography. But if there is any alternative, to transfer your pattern, maybe we can use soft lithography instead. Okay, so for the first soft lithography you're going to learn is the replica molding. Okay, first of all, by referring to the first diagram, master mold is replicated in PDMS. PDMS is a type of polymer, polydimethyl siloxane. Okay, polydimethyl siloxane or PDMS by casting and curing PDMS pre-polymer. So you create the master mold first. Okay, so here, for the exam purpose, if you say polymer, it can be accepted. Okay, don't worry if you cannot remember everything. Okay, you can put polydimethyl siloxane, you can put PDMS, or if you cannot remember at all, you just write down polymer. Okay, and then don't worry about also the dimension. Here we have the 15 nanometers, but you can put any what we call sensible or logical dimension you can put. Okay, so don't worry about this 15 nanometer. You can put 5 micrometers. Okay, it's okay. Don't worry about the dimension. The second one is that, after you create the master mold, you oxidize the master mold. Okay, the PDMS mold is oxidized in oxygen plasma for 1 minute and exposed to fluorinated silane for 2 hours to make a surface with low addition to PDMS. Okay, so after that, what you are going to do is that, you have to cast against this negative replica, cured and peel off. Okay, you cast against the negative replica, cured and peel off, and then after that you will have your positive replica of the original master. Yes, this is how you are going to do your replica molding. Okay, another technique of soft lithography is a micro contact printing. It's actually, the principle is more like a stamp, where you use the self-assembled monolayers, as an ink. Okay, in this technique, you use the PDMS stamp, this polymer stamp, to form patterns of self-assembled monolayers on the surfaces of the substrate. Okay, so the PDMS stamp is coated with an ink of the molecules. Okay, the PDMS stamp is coated with an ink of the molecules and pressed onto the solid surface. This ink is a self-assembled monolayer, and this will create a monolayer on the solid surface. Okay, so this monolayer will form your pattern of interest. So the use of elastomers, okay, allows the micropattern surface to come into conformal contact with the surfaces over large areas. So for this technique, don't worry, okay, it is more like a stamp. Okay, it is a stamp that creates a micropattern surface, okay, just like your what we call in our language chop. It's just like our normal chop. Okay, you have an ink that made up of these self-assembled monolayers. Okay, then you stamp it on the substrate, and then after that you will have your pattern of interest. Okay, another interesting technique is the micro transfer molding. Okay, here, okay, if you still remember, how do you play around with your potato, with carrot, or with cucumber during your kindergarten? Okay, your kindergarten teacher will ask you to play around with potato, okay, make a pattern, and then put a watercolor on it, and then you have your pattern, or you have your cat or anything, okay, and then you stamp the potato on the paper. So this is also the same principle, okay, the same principle with micro transfer molding. Okay, what happened here is that, okay, you create, okay, the PDMS, you make a pattern on the PDMS, okay, and then the PDMS stamp is filled with your pre-polymer. Okay, so this pre-polymer will act like your ink. Okay, so when you put your pre-polymer or your ink, then you remove your excess pre-polymer, your excess pre-polymer. Then, okay, like your potato, you press your stamp, okay, against the surface. Okay, you take your stamp, okay, you stamp out, you cure your polymer, okay, you cure your polymer, and then you peel off, okay, you peel off your stamp. Okay, so here you will have your pattern. Okay, for the final technique is the micro molding in capillaries. Okay, for micro molding in capillaries, the principle is also the same as your potato, your potato and ink, but the only difference is that you apply, okay, you apply the ink on the other side, okay, and then you make sure that the ink will go to the other side, okay, using maybe you use a vacuum, okay, maybe you have a capillary action, okay, to help for the ink to fill the channel or to go to the other side. Okay, so how does it done? You have the stamp first, okay, you have the stamp, you have the pattern, and you push the stamp against the substrate. Here you put the pre-polymer, okay, on one side of the stamp. So the pre-polymer is applied to the excess holes in the mold. Then the pre-polymer, maybe with the assistance of the vacuum, will fill the channel, okay, or it may be helped by the capillary force. Okay, then the polymer will be cured, and lastly you will peel off the PDMS mold, and then you get your pattern. So here you have all your soft lithography technique, okay, and after this we will go to another technique, which is the E-beam lithography. Okay, now I will introduce you to the E-beam lithography. Okay, E-beam lithography in some way is pretty much similar to photolithography, but the only difference is that it uses electron beam, okay, instead of UV light. Okay, so the source of the E-beam is similar to the scanning electron microscopy, okay, where you use the E-beam instead of the UV light. So here, okay, the equipment is made up from the SEM, okay, with a pattern generator and also alignment system. Here the parameter that you need to control, okay, the parameter you need to control the E-beam is the accelerating voltage, okay, operation current, exposure dose, and exposure dwell period. For slide 44, okay, and the steps involved in the E-beam lithography, okay, is the same, where you spin coat the substrate, okay, with the electron sensitive polymer resist such as PMMA, okay, or you can say that the E-beam sensitive coating, okay. Here is the difference, okay. You expose the polymer with electron beam, okay, and the rest of the process will be the same, okay. The most important and important and also the advantage of the E-beam, you can see the caption below, okay. You can create patterns at nano size, okay. So you can say that the beam diameter here applied here is 3 nanometers. So instead of normal photolithography that you got your like 5 micrometers, 10 micrometers, okay, maybe the most is like 3/4 of micrometers, maybe somewhere 750 nanometers and so on, okay. You get at like a single digit nanometer size of pattern. For slide number 45, you can see the application of electron beam lithography, how you can create patterns, okay. These are the examples, A, B, C, and D. So slide number 45, okay, wrap up the whole process regarding to the electron beam lithography, okay. So now we have finished the photolithography, and now we are going to go for another section which is the micromachining section, okay. So what is the definition of micromachining? So here is the basic, okay, the basic term for micromachining, which is the use of standard semiconductor process technologies in combination with specially developed processes to fabricate miniature mechanical devices and components on silicon and other materials, okay. So this is the term, this is the term for micromachining, and there are two types of micromachining techniques, which are bulk micromachining, meaning that you work the whole, okay, the whole substrate, okay, you work out the whole substrate, the whole chip, okay. Another one is only on the surface, okay, which is the surface micromachining. For slide number 47 up to 56, okay, we will discuss about bulk micromachining, okay. For silicon, okay, we can say silicon, okay, substrate bulk micromachining, okay. It is a process that involve partial removal. Only part of the substrate will be removed, okay, which create 3D structures or free mechanical devices such as cantilever, okay. Cantilever is one of a classic example of the structure that will be created by using micromachining, okay. Another fact, okay, in this slide which is important is that you have two types of etching, okay. So if you want to make this 3D structure, okay, you have two type of etching. One is wet etching, okay. You immerse the sample, okay, your substrate in a liquid chemical solution, and with the reaction of the sample and also the chemical, you will have your 3D structures. Another process you can use is by using dry etching, where you remove your sample, part of your sample, okay, to create your 3D structures by using physical means, okay. For example, your sample is sputtered or dissolved using plasma, okay. It is a reactive ions, okay, or a vapor phase etchant. So you will remove a part of your sample, okay, physically, okay, by using dry etching, which usually applies plasma, okay. For the wet bulk etching, okay, it depends on the crystal orientation, okay, crystal orientation, while dry bulk etching depends on the direction in the wafer. Okay, for bulk wet etching, okay, we have one term which is anisotropy. Okay, anisotropy is the property of being directionally dependent, okay, as opposed to isotropy, which implies identical properties in all directions. So in this, okay, in this slide, okay, we will create a structure or cavity, okay, with or without membrane, protruding structural pyramidal tips or mesas, okay. This mesas means like a plane, okay, like a plane, like a block on your chip, okay, on your samples, or suspended mechanical structures such as cantilever, okay. So this wet etching, it has a direction, okay, it has a direction. So usually, okay, with this, we will have a lot of application. We have a lot of application, such as, okay, we can manipulate this wet etching to create silicon pressure sensors, okay, accelerometers, neuron recording probes, and also probes for scanning probe microscopes. Okay, for slide number 49, okay, this slide tells you about what is wet etching, okay. What is wet etching? So we can say that in microfabrication, this is one of the simplest etching technology. You just dip your sample into a chemical, and then, okay, the silicon will dissolve. Okay. Here you need to select a mask. Okay, you need to select a mask which will protect your substrate. Okay, and this mask will not dissolve, or at least etches much slower than the material to be patterned. Okay, you can use other alternative. For instance, okay, we will see in the slide number 50. Okay, okay. Second point is that, okay, some single crystal materials such as silicon exhibit anisotropic etching in certain chemicals. So like in previous slide, okay, anisotropic meaning that it has certain direction, okay, it doesn't etch all part of the substrate. It has some, what we call some direction, okay, some direction that it will etch the substrate. Okay, so it has a different etch rate, okay, different etch rate in if you compare to the isotropic etching. Okay, so, okay, one of the example is that the 111 crystal plane side walls, okay, that appear when etching a hole in a 100 silicon wafer, okay, in calcium hydroxide, okay, in potassium hydroxide, you will have a pyramid shaped hole instead of a hole with rounded side walls with a isotropic etchant. Okay, for slide 50, okay, this is one of a good example, okay, of how a wet etching system is being done. Okay, you have silicon substrate, okay, coated with silicon carbide. There you etch the silicon carbide, okay, with plasma, which reveal the silicon surface. Okay, so this silicon surface acts like it's like a window, and then you have the silicon carbide unetched surface, which is the mask. Okay, then you dip it inside a potassium hydroxide or gallium hydroxide solution at 70 to 80 degrees. Okay, so what will happen is that, okay, this window shaped like a square, like a square, okay, or rectangle, but instead of having beautifully square or rectangle shape, okay, you can see in figure 2 you have A, B and C. Okay, we have some sort like pyramid. It's not a perfect square. Okay, you can see silver, okay, silver substrate, which is the silicon itself. This silicon is on the plane 1-1, plane 1-1, which will not be etched, okay, by the potassium hydroxide. Okay, but the 100 plane silicon will be etched away. Okay, slide 51. Okay, don't worry about this. Okay, please go and have a look at the table. Okay, there are 3 columns which are the materials used, okay, the etchant used, and also the etch rate. Okay, you can see that for the silicon, okay, in 100 plane, okay, the etchant is a gallium hydroxide or potassium hydroxide. The etch rate is that 1.4 micron, okay, the fastest it will be 1.4 micron per minute. Okay, and then you can see that, okay, certain type of like for silicon nitrate, if you put it inside the KOH, okay, it will just take 5 nanometers per hour. So the etch is very slow. Okay, so for EDP, okay, EDP is a ethylene diamine pyrocatechol. Okay, and then there's a small picture there. Okay, there's a small picture there showing a probe. So if let's say you just imagine your rectangular chip, okay, if you want to make this micro needles, okay, this micro probe, you can use, okay, if it is made from silicon, you can use a gallium hydroxide, okay, with a mask or something, okay, and then you cover it. Maybe it's a silicon dioxide, okay, it's a silicon dioxide on top of the silicon, okay, and then you dip it in the gallium hydroxide, and then you have your probe. Okay, so this is one of the example, okay, of application of bulk micro machining. Slide 52, okay, tells us about the dry or the plasma etching. Okay, so means that we just finish our wet etching for the slide number 51. Okay, dry etching, we use it, okay, we use it for faster and simpler etching, and it is more directional. Okay, and here we will use a highly reactive species and ions, and the species used will play a role. Okay, will play a role to make it faster and more directional. Okay, so now we have slide number 53. Okay, this figure depicts a typical RF powered plasma etch systems. Okay, so it has a few components that you have to remember. First of all, it has 2 electrodes, okay, Okay, it has 2 electrodes that will generate the plasma sheath. Okay, and then you have to draw the RF generator. You have to draw your matching networks, the RF power input. Okay, another important part is the gas inlets. Okay, the gas inlets, and then you have to got the ground and also the outlet of the gas. Okay, here, okay, the one of the important aspects of this slide is that you have to know what type of etching gas that you are going to use. Okay, for the purpose of examination, okay, one gas will be enough. Okay, like for instance, you can just mention that tetrafluorocarbon, okay, CF4, or you just mention CF4 as the etching gas. Okay, but in this drying etching system, okay, you can use SF6. SF6 is not SiF6, it's SF6. Okay, chlorine and hydrogen bromide. Okay, you can use it as a etching gas. You can even use argon, actually, argon, and even oxygen itself also can be used as an etching gas, and it is usually used to etch photoresist. Okay, another important factor in this slide, another important information in this slide is that, okay, you use a vacuum environment, which is somewhere like the pressure will be like 1 millitorr to 1 torr. For slide number 54, we can see that ion etching, okay, the physical etching by using ion etching method is much more directional. Okay, etching species ions like the argon ion, okay, and also the trichlorocarbon ions. Okay, it will remove the material by sputtering. Okay, so for this, okay, for this physical etching, it is not very selective, because it will, okay, bombard all materials or sputter all materials at about the same rate. Okay, physical, okay, sputtering can cause damage to the surface with the extent and amount of damage a direct function of ion energy. Okay, for slide number 55, okay, you will have this ion enhanced etching, or known as deep reactive ion etching. Okay, this process is assisted by the ion bombardment, which enhance the etching process. Okay, because, okay, during your typical etching, okay, you will have some debris, okay, of your materials. Okay, so by using the ion bombardment, okay, it will remove the etch byproducts. Okay, the etch byproducts, the coatings resulted from the etching. Okay, or it can remove the inhibitor, okay, that may be due to the indirect byproduct of the etch process. Okay, so the exact mechanism may happen at the same time. Okay, it needs both components for the etching to occur. Okay, it get the anisotropic etching and little undergating because of directed ion flux, or maybe it is due to the selectivity, due to the chemical components or the chemical reactions that is done. Slide 56, it is just one example of the application of both dry etching and also the wet etching. Okay, this is actually my PhD work. Okay, PhD work where I have to etch the silicon carbide layer. silicon carbide layer. So here the AZ4562, okay, is the thick photoresist that is applied on the 3C silicon carbide. Okay, so after that, okay, because the photoresist is thick, okay, it survive the reactive ion etching. Okay, however, okay, the thin, okay, layer of silicon carbide was removed. Okay, due to this removal of silicon carbide, the gallium hydroxide KOH, okay, can react with the silicon substrate, and then you can see the fourth figure. Okay, the fourth figure shows the silicon that had been reacted with the gallium hydroxide. Slide number 57 is about surface micromachining. Surface micromachining can be achieved by building microstructure by adding materials layer by layer on surface of the substrate. Low pressure chemical vapor deposition technique can be used as a deposition techniques, and polysilicon is a common material for the layer material. Okay, so the sacrificial layers, usually the silicon dioxide, are used in constructing the MEMS component, but are later removed to create necessary void space in the depth. Okay, so we will have one sacrificial layer, okay, that is being built at the surface of the substrate to achieve the surface micromachining. Slide 58. Okay, the surface micromachine typical three types components, which are the sacrificial component, which is also called as a spacer layer. Okay, it is usually made of phosphosilicate glass or silicon dioxide. Okay, the microstructural component material, which is popularly used, usually polysilicon, and then the insulator component. Okay, the etching rates for the sacrificial components, okay, the silicon dioxide or the phosphosilicate glass, okay, must be higher, okay, or much higher than those for the microstructural component or the insulator components. Slide number 59 is very important for the surface micromachining section. Okay, so first of all, we will have the step 1, which is the deposition of the sacrificial layer. Okay, then you pattern the sacrificial layer. Okay, after that you deposit the structural layer. Okay, which is the conformal deposition. Okay, then you use the liquid phase, okay, the liquid phase removal of the sacrificial layer. Then you remove the liquid and then the drying process. So you will have the pattern. But for the micromachining is the laser micromachining. So from slide 60 to 63, okay, I will explain about laser micromachining. Okay, laser micromachining we can say is you can say it's a bulk or surface, but we can say that it is more towards the surface micromachining. Okay, so you can create the microsite features using laser by removing excess materials. Okay, you can use it to cut, drill and weld the features required during microfabrication. So here the laser is controlled by switching the laser on and off, controlling the pulse energy, and by positioning the substrate or the laser focus. Okay, laser is emitted from the source, is passed through the energy attenuator. Okay, remember your X-ray. Okay, attenuator means that the energy will be weakened. They will be weakened. Okay, and then it is passed through the beam homogenizer. Okay, we will be homogenized. The beam will be homogenized. To homogenize the beam, the target illuminator and machine vision controls the beam to the focusing lens. Okay, the lens is moved by precision motion stages, and the beam is then forced on the workpiece and the machining takes place. So, okay, the point number 4 to number 6, okay, you have to relate it with the slide 61, which is the general setup for the laser machining equipment. Okay, slide number 61, okay, shows you the exact macro machine laser. Okay, it is used in ambience at Kuala Perlis, University Malaysia Perlis. Okay, so please, okay, refer to the figure. Okay, this is the general setup, and like I told you, each of the components, okay, in the equipment carries at least like half or even like 1 mark. So please do learn this diagram by heart. Okay. Slide number 62, okay, is nothing. It just show you the ability of the laser micro machining technique, okay, to create micro channel, okay, and then this is supposed to create a micro pattern. Okay, it uses 248 nanometer KrF excimer laser ablation, and this is a system, okay, aluminum on 3 silicon carbide on the silicon, okay, silicon chip. Okay, so for laser micro machining, okay, you need to know the terms, okay, for laser micro machining, the components of the laser micro machine equipment, and then finally is the advantages and also disadvantages of laser micro machining. Okay, the advantages of laser micro machining is a lot. Okay, if you can avoid photolithography. Okay, avoid photolithography because you don't use any solvent. You can directly transfer your pattern. Okay, it is a high speed and precision. You don't have to to have a mask alignment, all those development processes and so on. Okay, it is easily automated. Okay, forceless and contactless machining. So it is safe in certain ways. Okay, but the disadvantages is also you have to consider. For instance, it is expensive. Okay, it is expensive. Okay, and it needs highly skilled operators. Okay, not everybody can use it. Not all our like 37, 38 of us can use this machine. Okay, you cannot use something materials that is reflective. Okay, and then you have to make sure that the material used is not reflective, because if the laser reflected, can be very hazardous to the user. Okay, so for now we shall end the lithography and also the micro machining section. So we will continue with the other part from slide 64 until 80 onwards. Thank you very much.